do use our photo wall. And at this point, I will now uh, shift uh, the agenda to Bonnie Spring. Bonnie, like Donna, is a very well-known person in health behavior research. She's been past president of the Society of Behavioral Medicine, and like Donna, has been a mainstay of our training institute. But she has very particular nuanced insight into how teams come together. She actually runs the Northwestern CTSI. She's well known for her work on science of team science. And for previous mHTI, she's been working with our evaluative team on how these social networks form. And I've asked her to bring her personal experiences about team science to bear upon what you will undergo as you navigate these disciplinary silos and meet up with new friends and use common vocabulary but mean completely different things. So I've asked Donna to talk a bit more about the processes, the psychology, the fears, and the anxieties. Bonnie, are you there? Sorry.
I'm here. Yes.
Okay. You want to take over, Bonnie? Thanks again for taking
Sure.
on this responsibility.
And I have, before I attempt to get up my slides here, I have to say, every year we say that the fellows get better. This is unbelievable. Some of you are teams unto yourselves in terms of how many different training backgrounds you have. It's unbelievable. Life should be easy for you next year, Vivek. You've got your future mentors right here in this group, I think.
Well, Bonnie, I must say, I'm wondering whether I'm capable of leading this effort. They get smarter and smarter. Oh, well.
Okay. So can you see my slides?
Yes.
Great. Okay. So as Vivek says, you guys are going to be working in teams, and you have lots and lots of expertise and different kinds of expertise. And it's not easy working in teams. And so we'll talk a little bit about what kinds of things you might expect. So there actually is a science of team science, and we'll talk about what it is, why it matters, how to do it, and what sort of resources are available that might help you if you want to learn more about this. So two definitions. The classic definition of team science is that it's the integration of two or more scientific approaches to solve a complex, multifaceted problem. And you're all going to be doing that with a mobile health problem. That's the fancy definition. But the thing that people are usually most interested in is what we call team science praxis, or how to do it. And this is really how groups of scientists come together, get themselves organized, communicate, and conduct research. And the aim is to attain more than just additive impact, more than just what would happen if all of you sat in a room and engaged in parallel play. You want to create a whole that's bigger than the sum of its parts. So why do we need team science? Well, the consensus is that basically the volume of scientific knowledge has grown so much over time that it's become increasingly hard to have deep expertise in all of the areas that you need. And you can probably recognize this in your own experience when you try to keep up with the journals in your area. Just that alone is incredibly difficult to do. To keep up with multiple areas is really hard. And we think this is why we don't hear so much anymore about people like a Leonardo da Vinci. When you think about what he was able to do back in the 16th century, he painted the Mona Lisa. He made contributions to anatomy with the Vitruvian Man. He also he did engineering work on flight, on bridge development, and on weapons design. Not most of us couldn't pull that off today. And the other issue, I think, is that the problems that we face are really complicated. There are things like global warming, poverty, cancer, the healthcare crisis. These are not small problems that are going to be fixed by any one discipline or any one person. What they really need is the integration of these specialized knowledge bases that each of you has deeply. So we need to figure out how to accomplish collaboration among people from different specialties. Scientists have been kind of moving their feet in this direction, and the funding agencies have been scampering to catch up. So what you see here is that research is increasingly being done by teams. Whoops, sorry. Used to be that a single individual could accomplish their science alone. And to a certain extent, this is still how things are done in the arts and humanities, this blue line, done by a team of one, and that's stayed pretty constant. But if you look at science and engineering, patents, the social sciences, the proportion of research that's been done by teams has been increasing, and the size of those teams has been growing. In the last 50 years in social sciences, the number of publications that are authored by teams rather than a single person is more than doubled. Another thing that's been happening is that research is increasingly more geographically distributed. So again, we look at the red line here. This is single authors. They are declining in all fields except for arts and humanities. Within school, collaborations are staying flat. Across school, between school collaborations are going up. Why? Well, this is one of the reasons to pay attention to team science. It's because it has an impact advantage. And by and large, multi-authored publications, multi-university collaboration publications have higher citation impact factors than their comparable peer publications. That's not to say that's the only thing that matters, but if you're in an academic job, it will matter to a certain extent. So what you see here is anything above 0 is an impact bump up compared to a single university publication. And you can see that it's particularly high in the social sciences. Here is another way of looking at this. This impact factor bump up, if you look at the elevation here, it's particularly high if you're at a top tier university. It goes down a little bit as you go lower down the tiers. If you're at a low tier institution, you don't see that bump up at all. But if you want to have citation impact, this is one way of engineering it. The other reason why you should care about this is that to a certain extent, the federal funding agencies have moved your cheese. They will no longer fund or rarely fund single investigator research. They increasingly are funding interdisciplinary team science research. So NSF, which some of you will seek your funding from, has a smaller budget than NIH, but it's not trivial. And if you take a look at what happened between 1982 and 2010, take a look at what's happened to the distribution of single investigator versus multi-investigator research. 88% single investigator and 82, only 12% multi-investigator, and that has flipped in 2010. Even bigger bucket of funding at the NIH, the 2003 NIH roadmap was really designed as a fundamental change in the agency's research culture. They deliberately wanted to shift away from the traditional model in which they had supported only single discipline research. So what they're doing is this. And this actually was a very common slide that was shown around the time that the roadmap appeared. They want to shake up the disciplines, mix them up, and come up with something innovative and new and very forward moving. And you see this in terms of multiple publications that came out of the National Academies of Science, Engineering, and Medicine over the years. Starting in 2005, you see this, the one on convergence in 2014. That tends to be what team science is called in the physical sciences. And then most recently, a very important volume on doing team science in 2015. So what are they aiming at? What are they trying to accomplish with this, this shaking up of the disciplines? Well, there are different levels of team science. I mean, to some extent, if you're working with a group of people, it's a team and you need team science to communicate with those people. But there are degrees of difficulty in how challenging that's going to be. So you might think of it as if you're working in a unidisciplinary team, you might be working with people all from your same field. You have slightly different specialties. You may know more about one thing than your colleague does, but basically you were trained in the same paradigm, so it's not all that difficult. When you're working with multidisciplinary research collaborations, you've got more than one discipline, and you certainly have that at the Institute. We have medical folks, we have social science folks, we have computer scientists and engineers, we have communication specialists, and the sort of the natural formation that happens in multidisciplinary research is that the disciplines sort of go to their separate sides. They divide, and each does work. They do different work, but they don't really integrate until the end. They work sequentially. It's as if the accomplished product is then thrown over the transom from one discipline to another, and that new discipline takes it from there. So, for example, one of the ways that mHealth can be done is one group of people develops the sensors. Another group of people programs the code to transmit the sensor signals to a receiving device. And then it goes from there. Somebody uses this for an intervention. By the time that we go to the higher levels, the levels that are really aspirational, we hit either inter or transdisciplinary research. Now we're talking not just about collaboration, but about an integrated research team. Interdisciplinary research, once again, involves more than one discipline, but now the two disciplines they align more closely. There is an effort to engage more frequently, to communicate more regularly, to understand better what the other person's methodology is, to be able to communicate with the deeper understanding. By the time that you get over here to transdisciplinary research teams, you have developed a new entity. You no longer are the blue and the red team. You have now morphed into the purple group. And you've done that by a process that involves not just sitting in the room and passing products back and forth, but really trying to engage with people from the other discipline well enough that you understand their language, their methodologies, their goals. You're aiming at a shared mental model of what you're trying to do. And I will give you an example, a personal example that just happened to me recently. So I used to chair the behavioral medicine study section that reviews NIH grants. And so I had done that for quite a number of years, and I had a pretty good sense of what they funded. But I also collaborate very closely with the statistician and also with the computer scientists. And we had a grant that we assembled together. And this grant was about habit formation and measuring that. It involved extending a statistical method, and it also involved a bit of machine learning. That was the third aim, so it was a small thing. Well, we sent this grant to the study section that I'd chaired, thinking, well, I know their mental model just fine. Well, it was not discussed. I was not very happy about that. But then the question became, what had we turned into? Who was ready to review us in this new sort of compilation that we were in? And we shopped all around, ran there's a program you can submit your abstract to, and it recommends study sections. And it turned out it recommended that we go to a computer science study section for a grant about habits. Okay, we went and we got funded the first submission. So I think this is probably good. It wasn't fun at the time, but I think it shows what we're trying to do. We're trying to come up with the new sciences that will give us the nanotechnologies, the bioinformatics, the neurosciences that are neither neuro or biology. They are both. They're an amalgam that didn't exist before. So coming into why is it hard to do team science? And some of it is just the plain old fact that we're dealing with people. And sometimes they are the hardest part of doing team science. So take a look at this pairing, which is one that you'll probably work with in this institute. So you have medical folks on one side, and you have a computer science team on the other side. So take a look and see if you see differences between them. Is it just language, or what other differences do you see? Well, probably you're going to see several things. One is in medicine, you've got a culture of suits and ties. In computer science, jeans and t-shirts are the traveling clothes. In medicine, the primary value system is commitment to the physician's oath, first do no harm. In computer science, it's the commitment to search for the truth. And if some things get broken in that process, well, if you're searching for the truth, maybe that's okay. In medicine, you have a culture of respect for hierarchy and expert authority. In computer science, you have a culture where people are encouraged to critique the accepted wisdom, not necessarily to accept the expert authority. And in medicine, a lot is driven by the fact that errors can be mortal threats. You don't make them lightly. Whereas in computer science, by and large, they're inevitable. They're just a sign of the creative process. So these are really very different ways of thinking about what you're doing. Nobody trained you in these things when you were in your graduate school or your postdoc, but they sort of come along for the ride as you assimilate to the culture of your field. And it can lead to some real challenges in communication. So as social scientists or psychologists, we tend to use theories with a lot of abstract terms like outcome expectancies and perceived severity. And when we're working with engineers or computer scientists, they may say, well, what can you take a function of that? Can you do a square root of it? Is it quantifiable in some and relatable to something else in a very lawful way? This actually is something that you will probably bump up against. And I just flag it here so you can recognize it if you happen to fall into this and there's tension for some reason that's not apparent. So as behavioral scientists, we tend to think first, you're being right with God if you start with a theory or a hypothesis or a model. And that is supposed to indicate how you design your study cleanly to test that hypothesis. You care about internal validity. You collect your data and you analyze it statistically to see if it confirms your hypothesis. And if it does, you say you've emerged with knowledge. If it doesn't, you go back and you maybe tweak the theory or the model and try again. If you're a computer scientist, you start with data and you mine the data to emerge with your hypothesis. And your hypothesis you can think of as a model or an algorithm that is characterizing the nature, the features of that body of data. That's your knowledge. Now think about how these two different approaches look from the opposite field's vantage point. And I have sat through some almost food fights about these issues. So as a computer scientist can view behavioral science, this can be these imprecise, non-mathematical theories. You're not quantifying relationships among things. What is this? It's metaphors. You're doing statistical analyses. These models are making assumptions about data, that their distribution, that things are normal, that errors are randomly distributed. Well, we know those assumptions aren't right. It's a sort of a cookie cutter approach. Sometimes the biostatisticians that you'll seek out are seen in data science fields as the biostatistician police. They tell you what you can and can't do. They're no fun. There's no discovery in the field. There is no really new emergent knowledge. And you're publishing in journals. Why would you do that? By the time that something passes peer review and gets into print, the knowledge is antique. Now flip it and go over to how many behavioral scientists can come in with a bias towards computer science. I say this having, when we recruited my computer science colleague a number of years ago, the first thing that we said to him is, we would give him a challenge to design an experiment. And we would come back at the end of the day planning to discuss the research design. He would have an answer to the question. How did you do that? You didn't even design the experiment. He found a data set and he mined it. We see that as fishing. He's not being driven by a hypothesis that he will confirm or refute. He may build an accurate data model, but it's unique to the data set and it's so complex that it's not interpretable certainly not to a clinician. He's not building theory. He's not building a cumulative body of knowledge. And we see it as all exploratory. So they are different points of view and they get you different benefits, but they are different. We actually wrote about this when my colleague Nabil Ashraf, the computer scientist, first came to work at Northwestern, trying to discuss some of these differences in how the world looks from the medical science and the computer science sides of the house. And now getting down to what is likely to happen during the course of the week. Well, actually, I say the week. It used to be a week. Now it's over the course of the many weeks that will constitute the Institute. At the beginning, things are likely to be quite lovely. We call this the stages of forming a team. Everybody is on their best behavior. You're all being very civil, very respectful, and that's all great. That's where you need to start. But you need to get to this next stage that Tuckman called storming. And this is a stage where you've gotten engaged in deep enough conversation to realize some of the places that you differ, just like the examples I was just giving you of how computer science can look from behavioral science perspective and vice versa. You've got to engage enough to learn where something just doesn't look right from your perspective. And because we're passionate about the science that we do in our methodologies, there can be some heat generated. You then get through that, and the advantage is you emerge at a deeper level of understanding. We call that norming. And then your best performance will usually come once you've developed some shared vocabulary, some shared mental model of what you're doing. You can articulate the goal, you can understand how it looks to another person, and then you carry on. So that the place that things can be the most difficult is around this issue of productive collision or conflict. It really is necessary in interdisciplinary work if it's going to become transdisciplinary. Productive collision is a process by which parties who see different aspects of a problem can constructively explore their differences and search for solutions that go beyond their own limited vision of what's possible, because we all have a limited vision. That's why we need to be in these interdisciplinary teams. And people temperamentally will differ on whether they are wanting to contain the conflict or push the envelope and foster the disagreement. This is a balancing act, and one hopes you will dance around with it during the course of the week. You don't want anything to get out of control, but you do want to push the envelope a bit so you learn some new things. So what are some of the things that facilitate team science? Very important to be willing to ask dumb questions. This is one of the most amazing things to watch among very senior scientists who do well at this. They ask some of the simplest questions. They look really stupid, but they're in fact quite profound. You've got to have communication, proximity, or at least regular access. It helps if you've got shared values, but failing that, at least a commitment to communication on a regular basis. It helps if you have institutional policies that value team science. This can be tricky because you are likely to be engaging in mega multiple authorship papers. And some institutions understand the value of people who are participating in a team and maybe middle authors on a fair number of papers. But they're vital to pushing the science forward in that institution. It also helps to be able, when you're having a disagreement, to be curious in the face of that, to not sort of get all emotional and bent out of shape, but to be puzzled about why it's happening. Some of the things that hinder team science, a lot of sensitivity to loss of power, loss of face, loss of status, sort of the opposite of the willingness to ask dumb questions. Another barrier can be the assumption that there is just one single right scientific method. There is one correct vocabulary, one correct theory, one way of doing analysis the right way, and only one publication venue. That it's got to be journal, it's got to be conference, can't be both. Strong conflict avoidance can also be a problem because it protects you from some of the debate that would be helpful to advancing your understanding. And sort of the opposite of curiosity in the face of disagreement, that when you're not understanding what's going on, you become mistrustful. So giving something the benefit of the doubt is a real advantage. In terms of resources that you might find useful, this is actually for an online website, a series of team science modules that I developed with funding from the Office of Behavioral and Social Science Research and the CTSA. There's if you want a sort of an encyclopedia on the science of team science, on videos from some of the gurus in this area, reviews of some of the concepts and the main bodies of research, and also these very interactive modules in either behavioral science or biomedical science or clinical medicine. And here's what that site looks like. It's www, well, actually, it's just plain old teamscience.net. You can find it. You do need to register, but you don't. It's free. You don't pay anything, and it's just there for your use. And I'd like to thank you for your attention.